Question is, a uniform plane wave in air partially reflects from the surface of a material whose properties are unknown. Measurement of the electric field in the region in front of the interface yield 1.5 meters spacing between the maximum and the minimum, with the first maxima occurring at 0.75 meters from the interface. A standing wave ratio of 5 is measured. Determine the intrinsic impedance of the unknown material. Here, the spacing between the minimum and the maximum is nothing but, in general, here, suppose if we consider the field is in this form, this is the minima, this is the maxima, the distance is lambda by 2. Here, this is minimum point, whereas this is maximum point, where the field has its magnitude maximum. Here is the minimum. Now means lambda by 2 equals to 1.5 meters. That means lambda equals to 3 meters. If we know the lambda, we can decide what is the frequency of operation, that is c by lambda, that is 3 into 10 power 8 meters per second divided by 3 meters, which is nothing but 100 megahertz. Again, the one more data given in the problem is the first maximum is occurring at a distance of 0.75 meters from the surface. And suppose if we consider this is the load end, here the distance where first maxima is occurring, this distance is 0.75 meters. Means the minimum is occurring at the load end, because this is 0.75 meters is nothing but lambda by 4 meters, which is equals to 0.75 meters. Means the minimum is occurring at the load end. That means the reflection coefficient gamma is negative as well as real. Here the reflection coefficient gamma equals to s minus 1 by s plus 1. We know the standing wave ratio. S is the standing wave ratio here. S is 5 here. 5 minus 1 by 5 plus 1 means 4 by 6, which is equals to 2 by 3. Means gamma equals to minus 2 by 3, which is equals to eta minus eta naught. Means this is the intrinsic impedance of the material. This is the intrinsic impedance of the free space. Eta plus eta naught. So from this equation, intrinsic impedance of the material is intrinsic impedance of the free space divided by 5, which is equals to 75.4 ohms. The option B is correct here. So the question is, it is desired to estimate a stationary random process S of t with power spectral density S of f equals to 1 by 1 plus f square, comma, given a observation, that is given a noisy observation S of t plus n of t, where n of t is additive white noise with power spectral density equals to 1. Assume that S of t and n of t are orthogonal. Full stop. The transfer function of the optimal MMSE filter is, here the transfer function is given as power spectral density of a stationary random process, that is SS of f, divided by a noisy observation, that is SS of f plus Sn of f, that is nothing but 1 by 1 plus f square divided by 1 by 1 plus f square plus 1. Here 1 by 2 plus f square. That means the answer C is correct. Here the question is, a binary PAM communication system employs a rectangular pulses of duration TB and amplitudes plus or minus A to transmit digital information at a rate of 10 power 5 bits per second. If the PSD of the additive Gaussian noise is N0 by 2, where N0 is 10 power minus 2 watts per hertz, the value of A that is required to achieve a probability of error equals to 10 power minus 6 is. Here, since the rate of transmission R equals to 10 power 5 bits per second, means the bit duration TB equals to 1 by R, which is equals to 10 power minus 5 seconds. The probability of error in PAM is equals to Q of under root 2EB by N0, which is equals to 10 power minus 6. That is possible if and only if 2EB by N0 equals to 4.75. We know EB equals to A square TB. Now from this, EB equals to 4.75 square into N0 by 2. Then A square TB, which is equals to A square TB. Now from this, if we solve this one, we will get A as 106.21, which is option D is correct. Here the question is, a communication channel has a bandwidth of 100 kHz. This channel is to be used for transmission of an analog source M of t where magnitude of M of t is less than 1, whose bandwidth is 4 kHz. The power content of the message signal is 0.1 watt. Find the ratio of the output SNR of an FM system that utilizes the whole bandwidth to the output SNR of a conventional AM system with a modulation index of 0.85. Here we know a signal to noise ratio of FM to the signal to noise ratio of AM is equals to 3 into modulation index of FM whole square by modulation index of AM whole square, which is equals to 3 into here bandwidth of an FM system equals to 2 into that is FM, that is the maximum frequency or the bandwidth of the message signal. Here equals to channel bandwidth is given as 100 kHz, 2 into beta f plus 1 into 4. Here from this beta f we will get as 11.5. We know the modulation index of amplitude, that is beta am equals to 0.85. If we substitute these two values in equation 1, we will get the ratio in dB as here this we will get as 27.3967 dB, which is the option C is correct. The question is match the least one with least two. Here there are two types of MOSFETs, N channel MOSFET, P channel MOSFET. If we want to operate N channel MOSFET in enhancement mode, that means if VGS increases, the current has to increase, whereas in depletion mode, when VGS increases, the current has to decrease. See here, if for N channel enhancement MOSFET, the VGS is positive. If VGS is positive, ID increases if VGS increases. Whereas for depletion MOSFET, when VGS increases in negative way, the current has to decrease. So, according to the explanation, for the P channel N channel enhancement MOSFET, P equals to 1 matches, Q equals to 2. Whereas for P channel MOSFET, we can operate P channel in both the ways, that is enhancement as well as the depletion. So for enhancement VGS must be negative. So option 4 is correct, whereas For S, that is p channel depletion MOSFET, option 3 is correct. Hence, P1, Q2, R4, S3 is the correct answer.